Hello, everybody. Thank you very much for coming. My name is Martin Kleppmann. I would like to talk about database transactions. And when I proposed this talk, I went through a few potential titles that I could use, and I eventually settled on transactions, myths, surprises, and opportunities, because it at least has a bit of a feeling of optimism in there. My actual working title for this was more something like Transactions, Joys, Challenges, and Misery, with maybe a subtitle of Consistency Guarantees. You want consistency guarantees? Consistency guarantees! So, you see, looking at this topic has driven me a little bit insane. And it's possible that the forbidden knowledge in this talk will drive you insane, too. So this is a little experiment to see if I can drive a few hundred people insane within the space of about 40 minutes. This talk came out of some research I did for this book that I've been writing for ages and which still isn't finished. But this talk is kind of an extract of Chapter 7 from this book called Designing Data-Intensive Applications. You can find chapters 1 to 8 of this in early release at dataintensive.net if you're so interested. Anyway, when we're talking about transactions, I should really briefly go back into the history of where they actually came from. And the origin is kind of back in the mid-70s, when at IBM they were building what is now regarded as the first SQL database called System R. And this really laid the ground for a lot of subsequent relational database systems. And if you look at the style of what all the common relational databases now do, a lot of the ideas there can be traced fairly directly back to System R, actually. And the idea of transactions that you got in System R was then kind of kept for the next, 30 years or so, until around the late 2000s or so, this NoSQL thing started becoming a big movement. And then, of course, the inevitable counter-movement came back again, where people called it NoSQL, a new SQL, whatever that means. But really, these things are less about SQL and more about transactions, I have the feeling. So exactly which query language you're using and which data model is kind of relevant, but really the transactional guarantees of the databases are what most differentiates these different technologies. And so, of course, if we're talking about transactions, we're talking about ACID, which has been mentioned many times, but I do actually want to unpack what this means in a little bit more detail, because we kind of generally think we know what it means. We think we know it means atomicity, consistency, isolation, and durability. But what do those words actually mean? And if you look at it in a bit more detail, you kind of realize that they're a bit vague. Eric Brewer put this very politely when he said ACID, as a term, is more mnemonic than precise, which is a polite way of saying it doesn't really mean anything precise. It's just kind of this marketing term that we use. But nevertheless, there is a certain amount of definitions associated with these things. Let's start at the back with durability. That's kind of the easiest. Back in the day, durability meant you wrote your transaction redo log to an archive tape. And because disks were not that reliable, and so you could be sure that whatever you wrote to the tape, you would simply append all the transaction logs sequentially to that tape, and if your disk died, you could replay the tape and thus restore the state of the database. But then, of course, tapes fell out of fashion. We got disks instead, and then people started defining durability as meaning, oh, the database f-syncs to disks so that you don't lose data if something crashes. And then more lately, that's kind of been replaced with replication as a new way of thinking about durability. But that's really all I'll say about durability. Otherwise, there's nothing too interesting there. What about the C, the consistency bit? Now, it should hopefully be clear that the C in ACID is absolutely not the same as the C in the CAP theorem. If somebody comes up to you and says, we can't have ACID because CAP theorem says so, then I suggest you very quickly run in the opposite direction, because you're probably not going to have a very productive conversation. So I wrote this paper about CAP in analyzing it in a bit more detail if you're interested in it. We discussed it last night. I'm not going to go into detail today. So this C in in ACID is kind of an odd one in that it doesn't really have the same kind of structure of property as the A, the I, and the D do. Joe Hellerstein suggested that it was kind of basically tossed in by the authors to make the acronym work, but they didn't really attach much importance to it. So C is now generally associated as the database, the transactions the application executes on the database move the database from one consistent state to another, where consistent state here is defined through it meets certain invariants. And those invariants could be expressed as integrity constraints that are checked by the database, but they might be implicit as well. So like in an accounting system, you might have the invariant that all of the credits have to sum up to all of the debits, or something like that. And in some systems, you can express that kind of invariant declaratively, and others not. But generally, the odd thing about C is that it's really a property of how the application uses the database. It's not a property of the database itself. So that's why we won't really go into consistency in too much more detail either. What about the A, about atomicity? This is a kind of confusing one, because in the context of multi-threaded programming, if you're talking about concurrency there, you have things like an atomic increment, and that means that you can have multiple threads incrementing some value, and you're not going to have lost updates due to reading, delay, writing. But in the context of ACID, A, the atomicity, is not about concurrency, confusingly. The concurrency is dealt with under I, under isolation. We'll come to that in a minute. So here, in the context of ACID, atomicity is about how faults are handled. If things crash or things go wrong, what atomicity provides is that you're going to get either all or none of the writes that happen during a transaction. So you can think about this, for example, like this. Say some timeline here, time moves from left to right. Say you've got an auction website, and somebody has just won an auction, and so you want to do several things now with the winner of that auction. You want to update the listing to say, oh, the buyer is the user who bought it, and you probably want to send the buyer an invoice and maybe some other things as well. And now those are several writes that have to go to different places. And what happens if something crashes halfway through making those various changes? You could now end up in some inconsistent state where some changes have been made and others not. And the whole point of atomicity is that if you wrap these things in a transaction, you can say, OK, the incomplete changes due to the aborted transaction will be rolled back and won't be seen. So fundamentally here, this means transactions are about manipulating multiple objects as one, but doing that as one unit. So if somebody has transactions, claims they have transactions, but actually it's just operations on a single object, like a single document in a document database, for example, that's not really a transaction, because the whole point is that you can wrap several different mutations in one logical unit, and if something fails, roll back any partial modifications that you've made. So if I was reinterpreting the terminology rather than atomicity, I would actually call this abortability, because that's really the key feature of a transaction, is that there's always the possibility that it can abort, and there's well-defined semantics of what happens when it aborts, namely all of the writes that it made, all of the side effects are null and void and rolled back. So the nice thing about aborts is that they allow you to collapse a whole range of different failure classes down into just one thing that you have to handle. So it doesn't matter whether the problem is a deadlock due to concurrent transactions locks, or a network problem, or maybe some integrity constraint is violated, or maybe an application server crashed, or maybe a database server crashed, or somebody yanked out a power cable. It doesn't matter. All of these things all just collapse down to a single thing that you have to handle, which is an abort. And you could, for example, then retry the transaction. So that's all about atomicity. So let's move on to the isolation, which is kind of the most tricky of all of these, which is why I've left it till last. If you read the database textbook, it will say that when you mean ACID isolation, you mean serializable isolation, which is a rather strong definition of isolation. It means that the effect of all of the transactions is as though they had executed serially, one after another, on the database. That is, each transaction feels as though it has the entire database to itself, even though actually other things might be executing concurrently, but those concurrent things are never visible to the transaction. But in practice, there is serializable isolation, but there's also this whole raft of different isolation levels. And the history of these can actually be traced directly back to System R, where they first implemented serializable isolation, and they realized it's kind of slow. So what do? Well, let's fiddle with our lock implementation a bit, and let's just change some of the locks so that they're not held for so long, and then let's give those levels with different lock configurations names, and that's where these names come from. But really, the definition of these is in terms of a 1970s database's implementation details. And that's why these things are so hard to understand, because they're not defined as something that should make intuitive sense. They're just defined as implementation details of a particular database. So is there anyone here who thinks they can explain off the top of their head precisely what is the difference between read committed and repeatable read? Anyone want to volunteer? So if the assembled bright people of Strangeloop cannot tell the difference between these different things, even though I assume all of you will have used a relational database at some point, so in theory, you should make an educated choice about what isolation level to use. But in practice, you don't understand what the difference is between the isolation levels, so how are you supposed to make a choice? So let me look at this a bit more detail. Here's a wonderful list that Peter Bayliss and his folks at Berkeley made, looking at what is the maximum isolation level that various databases support, and what is the default if you don't change the default. And if you look at it, the maximum level is serializable on only about half of them. So half of the database don't even support serializable isolation. And serializability is actually the default in only 3 out of 20 or so. So this means you have a lot of this complexity to actually think about if you want to write an application using one of these databases that doesn't have race conditions. Let me go into the differences between these in a bit more detail, because I think it's actually quite useful to look at some examples of race conditions that can occur at these different isolation levels. And thus, we start then unpacking a bit more what we actually mean with isolation. So I'll start with read committed, which is actually a fairly easy one to understand. And it kind of means mostly what you think it should mean. Sorry, I skipped over a slide there. It's read committed means that two phenomena, two anomalies, are not allowed to ever occur. So these two things are prevented by the database. Those two things are dirty reads and dirty writes. Dirty reads is fairly simple. It simply means that one transaction reads data that another transaction has written but not yet committed. So that's what read committed means. Yeah, you only read the data once it's been committed. That's fairly clear. Dirty writes is maybe not quite as obvious. Imagine you have, this could be, again, the auction website example, for example. So you've got two transactions, A and B, and they are writing to two different keys in key value store, or two different rows in a relation database, whatever, and they're called X and Y. And they concurrently write to both of these. And the idea is that you end up with either X being A and Y being A, or you end up with X being B or Y being B. Those are the two things that could occur in a serial execution. But in this execution, you actually end up with X is first set to A, then set to B, and the final value is B, whereas Y is first set to B, then set to A, and the final value is A. So these two are now inconsistent. But read committed prevents this. So this is already one type of race condition that you don't have to worry about. But we have all of these other things. So what do they actually mean there? There must be some other kinds of race condition that can occur at read committed, which these higher isolation levels prevent. Let's have a look at this one. It's called read skew. And the example here is, say, this could be an accounting system or a bank or so, and you've got two accounts called X and Y, and they have a starting balance of $500. And now you've got a transaction that wants to transfer $100 from one account to another. And so the way you do that is, well, you decrement the account X by 100, and you increment the account Y by 100. And now this is fine, and you end up with 400 and 600. Now consider you have concurrently running a read-only transaction. It's only reading the database, not changing anything. And maybe it's a backup process, or maybe an analytics query or something like this, which needs to look at lots of different keys in the database. And at some point in time, it reads Y, and it gets 500 back. And at some later point, it reads X and gets 400 back. And it's valid for it to get 400 back, because at the time when it's reading X, that transaction that did the transfer is already committed. So it's reading committed data. This is fine. But we've now got this weird inconsistency where originally there was $1,000 in total in the system, but to this orange process here, it looks as though there are only $900 in the system. So it looks as though $100 have somehow vanished into midair. And so if this is indeed a backup, well, you've got now an inconsistent backup. If you restore from this backup, your database is going to be meaningless because you've seen different parts of the database at different points in time. And this can happen under read committed. And note, like read committed is the default isolation level for quite a lot of those databases here. And in order to prevent this read skew anomaly here, repeatable read and snapshot isolation were brought in. They're two fairly similar looking isolation levels from a user's point of view. Implementation-wise, they're very different. In many cases, when databases now say repeatable read, they actually mean snapshot isolation, just to be confusing. And there are basically two ways you can prevent read skew. One is by taking lots of locks, and this is what SQL Server does, for example, if you use repeatable read, and this is what System R did back in the day. But more common nowadays is the snapshot isolation, which is implemented as multi-version concurrency control, MVCC for short. So this is what Postgres does, and MySQL does, and SQL Server if you use the snapshot mode, and Oracle if you choose the serializable mode. Note, this is not serializable, but they call it that anyway. So the purpose of snapshot isolation is this: if you're a transaction that is reading the database, you see the entire database as it was as of one point in time. So even if other writes are subsequently committed, that read transaction, even if it runs for a while, is not going to see those. And that's where the multi-version comes in here. That means the database internally keeps several different versions for a data item, and it'll present each transaction with the one that's appropriate to its time cut here. OK, but we're still not at the top. There's still a difference here between snapshot isolation and serializable. So can we find another example that lets us distinguish these? What do we need to do? Now imagine you have say an emergency dispatch service, so like an ambulance service, for example, and the service needs to ensure the invariant that always at least one doctor is on call. Because if no doctor's on call, no ambulances can go. So there can be multiple doctors on call, that's OK. And doctors can trade their shifts. So if a doctor's not feeling well, they can ask a colleague to take over for them. That's no problem. And now this is the transaction that will get executed if a doctor wants to go off call. So they say, I'm not feeling well. I click a button on the web interface saying, can someone else take my shift, please? And this transaction will first check how many doctors are currently on call. And if this number is greater than or equal to 2, then it's safe for that doctor to go off call. So then the database can be updated and say the doctor is no longer on call. It's a very simplified example, but it's enough to show a particular anomaly occurring. So in this, imagine you have this database, and there's 3 doctors, Alice, Bob, and Carol, and Alice and Bob are currently on call. And Alice says, oh, I'm not feeling well. Can I go off call, please? And the transaction says, yeah, OK, we have 2 doctors currently on call. It's safe for you to go off call. So she gets updated to on-call false. And then concurrently, Bob does the same thing. He's also not feeling well. And so, but his transactions also sees 2 doctors on call. And now both go through, both meet their condition, and now you've got a database in which no doctors are on call, and our invariant has been violated. So this problem is called write skew, and it really does happen. I made a little test case that shows in which databases, under which isolation levels it happens. And for example, in Oracle, you simply cannot prevent this unless you build in explicit like locks or materializing the conflict in some way where you really have to think about what you're doing there. So just hope that your ambulance service in your town is not built on Oracle, I guess. But the general principle of this write skew, it can happen in many different situations. The general principle is that you have a transaction which reads something and then makes some decision based on what it has just read. So in this case, the decision is, are there enough doctors on call? And then it writes its decision to the database. But different transactions may write their decision to different places in the database, and so they're not going to conflict. So just a simple lock is not going to pick up the fact that those transactions conflict. And the problem here is that with concurrent execution, by the time a transaction commits, the premise of the decision that this transaction made, that premise may no longer be true. And this would then be a serializability violation. OK, so we've worked our way up to serializable, and we've realized that there are some fairly subtle but important race conditions that can happen at these various different isolation levels. So how can we actually implement serializability? Well, for 30 years or so, the only real answer was use lots and lots and lots of locking. And this technique is called two-phase locking. I'll abbreviate it here with 2PL. And the way that generally works here is this. So whenever you read something, you then need to take a shared lock on all of the stuff that you've read. And the shared lock doesn't stop other transactions from reading it, but it does stop other transactions from writing it. So you can then be sure that once you've got that lock, and you hold that lock until the end of the transaction, then nobody's going to come and modify those things that you've read. And the important thing here is really that you do have to hold the lock until the end of the transaction, which leads to some serious performance problems. Say you've got a transaction that needs to read all of the rows in the database, like a big analytics query, for example, would scan everything. Well, that needs to now take a shared lock on the entire database, which means that nobody can write to the database until that transaction has completed. You're basically locking the entire transaction, the entire database for writes. And this is why all of these weak isolation levels came into existence, because people said, like, there's no way I'm going to lock my entire database for writes. It's just not going to happen. Fortunately, better techniques were developed. So in the late 2000s, kind of two competing approaches came up as to how we could implement serializability without two-phase locking. And I'll run through each of them briefly. So the first example is from HStore, which was an academic prototype, but then became VaultDB. The second example is from Postgres. So the first example is literally you can simply take all of the transactions and execute them in serial order, one after another, which sounds stupidly simple and obvious, but actually it's a really good way of making sure that your transactions are serializable, because by construction they are. There's no concurrency going on. So you simply take what would normally be these various interleaved threads of execution and turn them into a timeline. Of course, this is only going to work if you make each transaction really, really fast to execute. And this is why it took 30 years to get to the point of, of course, theoretically, people would have been able to do this for ages. But if you want to actually execute them in serial order, each transaction has to wait for all of the preceding ones. So a few things you need to do there is you probably need to have all of the data in memory, because waiting for disk to come back is just going to be too slow if you want to execute serially. And you probably also need to take the entire transaction and ship it to the database as a stored procedure, where the database can then just quickly execute it as soon as it's turn. You're not going to have an interactive client-server slowly back and forth over the network conversation, because that would just take far too long. But like this, if you can get your transaction executed within, I don't know, 100 microseconds, then you can actually get some reasonable throughput. And so this is the principle that's used in VaultDB. John Hugg gave a good talk about this yesterday, so if you didn't see that, you can check out the video. Datomic uses a similar transaction commit principle as well, I think. OK, so that's one way of doing it. The third way, which I find quite interesting, is you can detect any serialization conflicts and abort transactions. This technique is called serializable snapshot isolation. So it's based on snapshot isolation, which we saw earlier, but adds additional checks to it in order to make it serializable. And this is what is used in Postgres since version 9.1. And in the first instance, it actually looks a bit similar to two-phase locking. That is, you have locks that you take whenever you read something and whenever you write something. But the difference is that those locks don't block. So if somebody wants to write to something that has already been read, and there's a read lock there, that write is not blocked. It can still go through. These locks just record everything, take a little ledger, and write down, oh, OK, so this write from this transaction appears to conflict with this read from this other transaction, and just records all of those facts. And then at the end of a transaction, when it's time to commit, an analysis process happens, and it looks at the various conflicts that occurred and decides, is it safe for this transaction to commit? And if there's the possibility that this transaction would introduce a serializability violation, that transaction is simply aborted, and it has to retry. So this is an optimistic way of ensuring serializability. You're assuming that the conflict rate is not going to be too high, because if you've got a lot of contention, then you're going to have a lot of transaction aborts and restarts. But if contention is not too high, then this can work very well. In contrast, two-phase locking is the pessimistic approach. So it makes sure that you can never, ever get into a situation where transactions observe non-serializable outcomes, but at the price of preventing a lot of concurrency. OK, so that's our overview over these different serialization levels. There's still more to say, I think. So there's kind of a big elephant in the room, I feel, with all of these transaction models, and that is all of them work just within a single database. And generally, that database is assumed to be in one geographic location. But we're building bigger systems than this now. What about if you're doing microservices and you've got several different services, each with their own databases? What if you're doing stream processing, and so you've got these flows which take in input streams, produce output streams? What do transactions mean in this kind of world? So we've got here these various kind of boxes, and there's a cylinder inside each box. And the idea, generally what I've heard recommended with microservices, is that you don't try to share a database between several different services, because that would break a lot of the goals of introducing microservices in the first place. So you've got these wrappers of application code around each database. And if you're doing stream processing, well, the picture actually looks very similar. The difference is only with microservices, these arrows here are request-response, like RPC or REST type data flows. In stream processing, they are queues and message brokers. But otherwise, the structure is very similar here. And generally, what people do, what seems to be the recommended thing, is to draw a box around each of these services and say, this is a transaction boundary. Transactions only occur within one of these. And if it's using a transactional data store, sure, it can use whatever facilities that data store provides. But there's not going to be any transactions across different services. And there's a very good reason for that recommendation. And that is that if you wanted serializable transactions across multiple services, you would have to run some kind of atomic commit protocol. So these are distributed systems protocols which make sure that if you've got various different parties who are all participating in a transaction, various different services, either all of them commit or none of them commit. And protocols such as two-phase commit, three-phase commit, transaction managers, etc., they implement this kind of thing. However, as we saw earlier, the whole idea of serializability is that transactions appear as if they were in a total serial order. Now, you can execute literally in serial order or not, but that order is definitely defined. So whenever two transactions conflict, somebody has to decide which of the two came first. And this, from a stop. From a distributed systems point of view, this makes it effectively an atomic broadcast problem. That is, the problem of getting a bunch of messages to different nodes in exactly the same order. But the issue with atomic broadcast is that, from a theoretical and also practical perspective, it's actually equivalent to consensus. And there are deep connections between all of these three, between atomic commit, between total ordering, and between consensus. And consensus we can definitely do, but it's pretty expensive to do. It requires a lot of coordination between different services, because we've got to get them to agree on something. And people tend to not like doing things like two-phase commit in services, because it makes them very brittle, very sensitive to failures, because it only takes one service which is running slow or which is temporarily not responding, and then suddenly everyone else can't get any work done either. So it tends to amplify failures. This coordination makes systems very brittle, whereas the whole point of wanting to introduce several services was to make them more decoupled from each other, so you could have independent failure domains. The whole thing gets even more fun if they're actually distributed geographically, because if you're trying to do consensus over a wide area network with very high latencies, with very variable latencies, a lot of the current consensus protocols really don't do a good job at this. That's why people recommend run Zookeeper only in one data center, for example. Don't try to run it across different data centers. So we seem to be stuck in this place where there's no transactions across different services. But what do people do instead? So what I've seen recommended in the context of microservices is, well, you might have compensating transactions, for example. That is, you try to do something, and the service does it, and then you do something somewhere else, and that fails. And now you have to say back to the first service, oh, actually, could you undo that again, please? Because this other thing that was also supposed to happen didn't happen. And so now, in order to get back into a consistent state, you kind of have to do some cleanup afterwards, which looks somewhat like transaction abort and rollback, except that you're implementing it at the application level rather than it being implemented by the database in the infrastructure. Look at sagas, for example. There's a paper describing this kind of stuff. What do people do about integrity constraints in this world? So say you have, I don't know, a constraint like you can only ship as many items as you have in the warehouse. What happens if you accidentally accept more purchases than you have items in the warehouse? Well, you're going to have to apologize to some of the customers and say, oh, sorry, actually, we ran out. Here's a discount code for your next purchase, and we've refunded to you, or something like that. And this is reasonable. Like, businesses do this all the time. But you can think of these kind of apologies really as you have some integrity constraint, but you don't enforce it up front. Instead, you check after the fact whether the integrity constraint was violated. And if it was violated, then you fix it up again. So bringing this back to the ACID terminology, it seems to me like these compensating transactions are a bit like the atomicity aspect. We're kind of implementing aborts at the application level. And doing apologies is kind of like the C of ACID, in that we're implementing integrity constraints and validating invariants, again, at the application level. So this kind of leads me to thinking, you're going to hate me for this. This leads me to thinking that every sufficiently complex and large deployment of microservices contains an ad hoc, informally specified, bug-ridden, slow implementation of half of transactions. I have no evidence whatsoever to back this up. I'm just like asserting it boldly. So what about the I in ACID? So I said like compensating transactions are kind of like implementing atomicity, and apologies are kind of like implementing consistency. What about isolation? So take another example. Say you've implemented a social network, and I don't know, one of your users has just broken up with their significant other, and they're really unhappy, and so they go to your website and they unfriend their ex-girlfriend or boyfriend, and now, after that, they send a message to all of their friends saying how horrible this person is. And the intention of the user here is clearly that their ex-boyfriend or girlfriend does not receive that message, because they first did the unfriending, and then they posted the message. So like, if I was a user, this would make sense to me in my mental model of the world. Except now, if you've got the friends database handled by one microservice and the posting database handled by another microservice, this ordering information between these two events is lost. So you could have, for example, a notification service which listens to these, and due to some transient glitch in a network or so, the unfriend event arrives later at that notification service than the post event. So by the time the unfriend event arrives there, it's already sent notifications to all of the people, including the ex-boyfriend or girlfriend who was not supposed to get the notification. So the problem that we have here is that there's a causal relationship between these two events. And that causal relationship is implicit. The user hasn't explicitly told us that this posting a message to friend depends on the unfriending event. It's just implicit through their timeline. But in this microservices world, we somehow lost that information. Now, this leads us to some interesting area of speculation and or research, which is a similar thing, where at the moment, the way we're building microservice-based systems is just pure eventual consistency. Hopefully, it's at least eventually consistent. Maybe it might be perpetually inconsistent, who knows? But we can achieve eventual consistency, hopefully. We probably can't do serializability because, as I said, that requires you to do two-phase commit, a kind of variant of consensus, and so it just becomes too brittle, too fragile. So we want something in between which will still capture causality, which could still capture this kind of ordering of events and allow people to reason more in a logical way about this. And causality is quite a nice thing, actually, because if you think about what's going on in snapshot isolation, you know, where I said you get a consistent snapshot or at one point in time that a transaction can read from, well, what does a consistent snapshot actually mean? It means that it obeys causality. That is, that if you see one item in the database and that was written after some other item, then that other item must also be in the database. That's really what a consistent snapshot here means. And the interesting thing is this can all be implemented without requiring global coordination, without doing consensus. There are nice proofs which show that this is actually the upper bound of consistency that can be achieved without coordination. Whether we can do it efficiently is another question. There are other interesting proofs which show that you get quite a lot of metadata overhead if you want to track causality. But I think that's going to be a very interesting, fruitful area of research. Can we make causality efficient? So to summarize, we've got this hierarchy of different isolation levels, which we inherited from System R in the mid-1970s. And nobody really understands what they mean. But most people are using something somewhere along that hierarchy. A lot of people are using read committed, in fact, because that's the default on about half of the databases we saw on that list. But the interesting thing about read committed is it can actually be implemented without coordination. And even something slightly stronger, introducing causality in that, can still be implemented without global coordination. So maybe there's some kind of way we can still do transactions across some kind of microservices or stream processing architecture which will obey causality, which will obey read committed, but which doesn't introduce the whole overhead and problems of coordination. There's a lot of research going on in this area. I've got a totally oversized reference list for anyone who wants to read papers. This is page 1 of the references list. This is page 2 of the references list, page 3, and page 4. And so you can find them, all of the slides online. I've tweeted the link to the slides already. It's a big topic, and I've mostly described problems and not described many solutions, because many of the solutions are still unknown. But people are working on them. If you fancy working on them as well, please do contact me. As a final thing I wanted to say, I'm actually going to be giving away free copies of this book. O'Reilly have kindly printed off 25 copies, even though it's not finished yet, but of the chapters that are there so far. And I'll be giving those away in the lunch break at 12:30 down by the entrance. Otherwise, there's also a discount code if you want the ebook. And I think I'm out of time, I'm afraid. So if you want to ask me questions, I'll be around here. And thank you very much for coming.